Thanks for the organizers. I'm Huanqing Chen from Chicago. I work with Nick Nieding on reionization simulation. And today I'd like to talk about what can we learn from quasar proximity zooms during reionization. As the name suggests, the quasar proximity zoom is a region just surrounding a quasar where the radiation field is dominated by the quasar. Depending on the luminosity, this proximity zoom can extend to up to 10 physical megparsec. That is including a lot of large-scale filaments and halos. And because of the nearby quasar, this region experienced quite a different reionization history than the common field. So studying this region, especially the gases in this region, can help us understand how different reionization history impact the gas formation. And this is one of the big reasons that why the quasar proximity zooms are so interesting. So another big reasons that we love the proximity zoom is that this region can potentially help us constrain IgM properties, because we know that the size of the ionized bubble depends on the total number of ionizing photons and neutral atoms. So by measuring the proximity zone size, we can potentially constrain the IgM density, neutral fraction, as well as the quasar lifetime. The way to measure the proximity zone size is to look at their spectra. So here I show an example from Eiler's paper. And this is a pretty typical reionization epoch quasar. Although at the redshift 6, the universe is pretty already ionized, but because of the large cross-section of the Lyman alpha photons, as long as there is some trace of neutral hydrogen, we will still see the saturated absorption. And this is the Gamma-Petersen trough, usually observed in Z about 6 quasars. But thanks to the high flux of the quasar, the region surrounding it will have an exceptionally low neutral fraction. And this will appear in the spectra as this non-zero flux region. And this is a place that we can do a lot of interesting work on. And in the future, we will expect more and more high resolution spectra being taken from this reionization epoch quasars. And this motivates us to analyze this region in more detail. So in this project, we study proximity zone using the synthetic spectra. We obtain this synthetic spectra by post-processing Cosmic Reionization On Computer simulation. This CROC simulation has both a relatively big box of 60 co-moving megparsec, as well as high spatial resolution, and allows us to resolve the Lyman limit system, which is potentially important in modeling the proximity zone. And the simulation includes gas cooling, heating, star formation, stellar feedback, and the radiative transfer is also done on the fly and allow us to model realistically the gas neutral fraction as shown in the right figure. The simulation itself doesn't include individual quasar sources. So we obtain the quasar spectra by first identify a bunch of big halos, massive halos, and then draw sidelines centered on these massive halos, and then post-process them with 1D radiative transfer code. Just to show you some example, this is a sideline drawn from redshift 8. The upper panel is the neutral fraction, lower panel, the transmitted flux. And the black line shows the value before we turn on the quasar. So at redshift 8 in our simulation box, most of the IgM is still neutral, except for some bubbles surrounding big gases. And right after we turn on the quasar, after 1,000 years, the value become like what plot in the blue. So immediately the neutral fraction drops to -7 and 10 to -7, and then proximity zone appears in the spectra. And the dashed line here I show is a smooth spectra, and this is what in practice a measurement is usually done. It's usually defined as the point where the transmitted flux drop below 10%. So now I will click through to show you how this proximity zone evolved as the quasar shine longer and longer. So we can find that in a time scale of 10 million years, this proximity zone will grow to a larger value. And this is the case for the high redshift before global reionization. The picture will look pretty different if we look at the case after global reionization, for example, at the redshift 6. At that redshift, since the universe is already pretty ionized most of the place, so there will be no more such typical quasar I front, but the whole universe has dropped to the IgM has dropped to the value of 10 to the -3. And so the time scale for the quasar proximity zone to grow is set rather by the time scale for the IgM to reach a new ionization equilibrium. So I put them side by side to show how, for you to compare how this proximity zone evolve. As you can see that within a 0.1 million years, the proximity zone size already grow to a large value. And afterward, this doesn't change much since the ionization equilibrium is established almostly. So to summarize what I just showed, here I plot the proximity zone size as a function of quasar lifetime. So before reionization at the redshift like 8, the proximity zone grows steadily in the first 30 million years. But after global reionization, this proximity zone will only increase significantly in the first 0.1 million years. And this arrow bars here I show covers 68% of the sidelines in our sample. And we can see that at the redshift 6, well, most observations are taken. Most of the old quasars have a zoom size around the 4 physical map parsec. Interestingly, in observation, Ilas et al. 2017 has measured some quasar sideline that has very small proximity zones. And I encourage everybody to listen to her talk tomorrow. So how to explain the small proximity zone is always a challenge. One possibility is always that the quasar is very young, but this is not very desirable for a supermassive black hole to grow to such a massive value within the 1 gig year of the universe. So in my last slide, I'd rather show you how old quasars can have those small proximity zones. So we search for our redshift 6 quasar samples, and we find that 2% of the old quasars have an extremely small proximity zone that is more than 1 physical map parsec. And if we look closely, we can find that most of them shoot through a gas that has overdensity above 100. And then this dense and neutral clump of gas will shield the gas behind it. And most of the time, they will show up as damping wing in the spectra. And if we plot the overdensity of this cloud in the histogram, it will look like the right figure. And most of them hit the gas with the overdensity above 1,000 within the 5 physical map parsec. So here I show my conclusions. In a neutral universe, the proximity zone size will increase significantly in the first 30 million years. But after global reionization, the proximity zone size will only significantly increase in the first 0.1 million years. In our simulation at redshift 6, 2% of the quasar has a very small proximity zooms, and most of it because the Lyman limit system or Lyman alpha system on the way. And thank you. And I'm happy to take any questions.
Okay, thank you very much, Huanqing. So we've got some questions coming in on Slack. Okay, so let's start with a question from Hamza Padamanbam, who says, thanks, very interesting talk. Do you consider a duty cycle for the active lifetime of the quasar in your work? I thought
no, so yeah, right. So in our work, right now I only just use the light bulb model, just light up it, and then the result here is for the we have not turn off and turn on, but I think previously Fred has did some work on the flickering model. Yeah, it will be interesting, and I will look at more into it. Yeah, thanks.
Okay, and then a question from Enrico Garaldi, who asks, is the dense gas associated to the quasar host, something like a merger?
No, these are very far away from the quasar. So here is already at more than one physical megaparsec, which is not possibly associated with the quasar host.
And then a question from Garrett, who says, nice talk. How do you deal with the light travel time effects, the speed of light in the growth of your quasar near zones? How do you make sure they don't grow superluminally?
In this particular observation, the speed of light is kind of cancel out. So here I probably show you a schematic of this. So the light here I show skyline and the time. So if we assume this is the speed of light, then what we actually observe is the regions between this. So assume this is the light from I from this is the speed of light. Then what we see is kind of the time, the real time minus the retarded time. So in this calculation, this factor is canceled out. So we don't need to worry about the line speed of light limitation.
Thanks. So we've got time for just one more question. So it's a question from Sarah Bozeman, who asks, how dependent are your results on the mean IgM neutral fraction evolution?
So in our simulation, we kind of self-consistently model both the neutral fraction and the temperature. So we haven't looked into how varied reionization history affected, but we do have many boxes, and we can look into more boxes to see how this affected. So yes, good question.
Okay. Okay, thank you, Huanqing. So there's lots more questions on Slack for you to look at.